Okay, so there's lots of different descriptions of what we might tell you math is. I did some of the research that I did when I was a graduate student, had that question as one that was posed during my research sitting. And one of the popular descriptions is that math is problem solving. So you hope that a student leaves your classroom with the ability to solve problems better than they were did before, that kind of idea. Another really common one is this idea that mathematics is patterns. It's all about pattern or pattern recognition. And so those are actually the first kind of two sections in this problem-solving chapter overall. And so we're going to take a look at some explorations of patterns today. Some of these patterns you've probably seen before. Others of them I don't think you will have. So give you kind of an idea of some of the different things that people are looking at in terms of patterns. All right, so one of the words that we use in mathematics a lot is this word conjecture. You hear it used in science as well. A conjecture is a statement or a conclusion that has not been proven. So it would be like you saying, I have a conjecture about anything in your life, okay? It just means that's what you think is going to happen. My kids ask me all the time, what are we doing after school today? Or what are we doing this weekend? Or what are we doing da-da-da-da? I stopped telling them because half the time it doesn't happen. My conjecture is wrong. And then people start crying and it's just not good. So a conjecture is what you believe is the case. Okay, it's not necessarily been proven. Inductive reasoning, there's two different kinds of reasonings. There's inductive and there's deductive. So inductive reasoning is a method of making generalization based on an observation of patterns. For example, if I showed up at class 3 or 4 or 5 class periods in a row and I was running late, you're going to start to make a conjecture that Dr. Hans runs late, right? You don't know that for a fact, you didn't research anything, it's just your observation of that pattern. Okay, that's inductive reasoning. You take a pattern and you sort of further that pattern along. Okay? Deductive reasoning is the use of mathematical axioms, theorems, definitions, and you're able to prove it logically. Okay? So you'll see how this sort of plays out when we're working with mathematics and not just talking about general statements about how they're different. And then a counterexample is something that proves a conjecture false. So again, if your conjecture was Dr. Hans always runs late, and all of a sudden one day I show up 10 minutes early, I've proved your conjecture false. And that's all a counterexample is. It's an example that disproves what you thought was the case. All right? So we're going to be talking in this section a lot about sequences. And a sequence is just an ordered arrangement of numbers, figures, or objects. And small children start working with this. If you go to the store and you get these books that they have, your pre-K books, and certificates and these little workbooks at home, a lot of them have patterns in it. So they'll show something like triangle, circle, triangle, what comes next, right? It's a pattern, and they're using figures to do it. Or they'll do it with colors, and it'll all be circles, and they'll have red circle, blue circle, red circle, blue circle, and they'll say fill in the next 3 of them in the pattern. So it doesn't have to be numbers. We're going to be looking at mostly numbers, but your book has some examples of some patterns with figures as well. There's 2 different kinds of sequences that are the ones that you've most likely seen before. The first one is arithmetic. So an arithmetic sequence is a sequence where you get the next term by adding the same value every time. For instance, we looked just a moment ago at an even and an odd problem in your book, right? The one that you brought up, and it said P equals 2, 4, 6, 8, and then it was, what was it, E? Well, one was P, and it was E was equal, the other was equal to 1, 3, 5, 7, 9. Those were both arithmetic sequences. The way you got from the first number to the second number in every single case was added 2. Okay, so an arithmetic sequence, you add the same number to get the next part of the pattern. That number that you add, in that case, in that example, was 2. That's called common difference. Okay, so that number that you can successively add each time is a common difference. A recursive formula, this is a way of describing it the way I just did. I said, how do you get the next term? You add 2. Okay? But it means in order for me to know what the term 7 is, I had to know what the term 6 was. If all I know about my sequence is that I need the next term by adding 2, I need to know a term to be able to generate the rest of the sequence. Right? You have to give me both a term and this sort of pattern recognition that you're following. So that's what a recursive formula is a way of describing it like that. So you would say something like, if the 5th term is 7 and the common difference is 4, what's the next term? Right? So you have to have a description based on prior terms. The nth term, this is a way of describing it where you don't need prior terms. Instead, you have what we would call an expression, or you might inadvertently call it an equation. So it would say something like, our sequence follows the pattern n plus 2. Well, the first term, n is the number of term neurons, and the first term is 1 plus 2 is 3. So if you want to know the 15th term, you put the 15 in for the number n, or the letter n, and you can find it that way. You don't need to know the 14th term from the 15th term. I bring up Fibonacci in here because I didn't have a real good place to put it otherwise. Has anybody heard of the Fibonacci sequence before? That's nuts. If you haven't, it's okay. You're not going to see it real frequently. You should be aware of it because whenever it comes up, it looks sort of like, what? I haven't seen that before, and it's hard to recognize the pattern. So if you take a look at this, you don't get, adding the same number every time. If you tried, this would be 0, right? 1 plus, well, it'd be 0 is 1. But how do I get from 1 to 2? Well, 1 plus 1 is 2. That's not good. And now 2 plus 1 is 3. Okay, maybe I'm adding 1 every time, but then all of a sudden you've got 3 to 5, and that's adding 2. So it's not arithmetic. I don't get there by adding the same value every time. It's also not geometric, which we'll talk about in a minute, where you multiply by the same value every time. But here's actually how the Fibonacci sequence works. So what you do is you add the two prior numbers together. So what is 1 plus 1? 2. What is 1 plus 2? 3. 2 plus 3 is 5, and so forth. So in order to start this sequence, you evidently need the first two terms, don't you? So this has a recursive formula built into it. You have to know the two terms prior to it in order to generate the next term. And it continues, right? So just so that we make sure we're on the same page, what would the next term be? 34. Because 13 plus 21 is 34. This is called the Fibonacci sequence. And there's a blurb in your textbook about Fibonacci, and it gives you a little bit of history and information about him as well. He was a famous mathematician associated with this sequence. Now, I just mentioned a minute ago geometric sequence. So arithmetic, you add the same value every time to get the next term. Geometric, you multiply by the same number every time to get the next term. So if you took, for instance, let's take the sequence 2, 4, 8. I'll write it down because I'm not going to do it in my head very well. That would be geometric. Because I take a term, 2, and I multiply by what to get the next one? 2. I multiply by 2 to get 4, and then I multiply by 2 again to get 8, and 2 again to get so forth. So a geometric sequence is actually a sequence that is derived by multiplying successive terms with the same value. This value you multiply by does not have to be positive. It could be negative. In fact, you could do the same thing with the arithmetic sequence. You could be adding a negative number every time. So it could be positive or negative. It can also be fractional. So for instance, if I took a sequence and I did 1, 1/3, 1/9, 1/27, this is a geometric sequence as well. What am I multiplying by every time? Not 3, but you're close. 1/3. I'm multiplying the denominator by 3, right? Yeah, so I'm actually multiplying by 1 on the top and 3 on the bottom. I'm multiplying by the common ratio of 1/3. So it can be done with fractions, it can be done with positives, negatives. Done with negatives is pretty cool because what happens is the sign changes every time. So if you have this one right here, and instead of the common ratio being 2, it were -2, it would look like this. I'd have 2, -4, positive 8, -16, positive 32, -64. It would alternate signs every time because I'm multiplying by a negative. Along with this idea of multiplying by a term multiple times is the idea of exponents. So you guys have seen exponents before. It's an algebra concept. So if you have a base A and you multiply it by itself a whole bunch of times, that's an exponent. And the number of times specifically is the number of times that the exponent represents. So this n would be n times here. If n is equal to 0 and a is equal to, or not equal to 0, then a to the 0 is 1. And If it's not this semester, we definitely will talk about it when you take Math 2 about why that is actually true, and really not so much definition as it is a result of the properties of exponents. However, your book's presenting it that way at the moment, so we'll go with that. So if you have anything, notice it does say it is a natural number, so we're not talking about fraction exponents. We're not talking about negative exponents either at the moment. We'll talk about them next semester, okay? We're talking about up here, whole numbers. So we're having like 5. Well, so we have A, and so forth. All right, so we're going to do some pattern recognition. We're supposed to be finding the next 3 terms and deciding if the sequence is arithmetic or geometric. And then you notice this thing at the bottom, it says, is this inductive or deductive reasoning? So I'm giving you an example of each one of these so you can see what they look like differently. All right, so what do you notice on the first one? What would the next term be? 13. Then 16. And then 19. So just so that we've got an idea of what we just did, is this arithmetic or geometric? Arithmetic. Remember, arithmetic means I added. And what was the common difference? Plus 3. I add 3 every time to the next term. How about on part B? What comes next? 3, 6, 12. It would be 48. And what? It is 96. What is it? You're right, it is 192. Good job. Okay, so what did you do every time? Multiply by 2, which means is it arithmetic or geometric? This is geometric. And it has a common ratio then, right? Not rational. Ratio. Where we multiplied by 2, right? Is this inductive or deductive reasoning? Okay, so let's go back a minute and describe what those were. Inductive reasoning is making a generalization based on an observation of patterns. Deductive reasoning is using mathematical axioms, theorems, definitions, and undefined terms assumed to be true and logic for proof. Which one does this seem like? It is inductive. We took a pattern and we generalized it and we sort of pushed into the future what we think is going to happen next. All right? So this is actually inductive reasoning. Let's look at this one because it's a little bit different. On this one, you do not see a portion of a pattern yet. What you see is an expression that could generate a pattern, right? Now, there's good and there's bad in that, right? So I can't look at this and say, do you recognize the pattern? Because what they actually told you is this is going to create a pattern. But what we can ask you is then to create a certain number of terms of the pattern. So this is the first 5 terms. And so we're going to find those terms. And the way we find those terms is because n in this is representing the term number I'm on. So if I put in n equal to 1, that is my first term. If I put in n equal to 2, that is my second term. So if n equals 1, what is my first term? 11. What if n equals to 2? I have 16. N equals 3. It is 21. N equal to 4. 26. I'm supposed to do one more. N equal to 5. 31. Is this arithmetic, geometric, or neither? Which one is it? It's not geometric.
Either.
It's neither.
Because we have 5 each.
Okay, it's arithmetic, but you guys have to tell me why. Oops. What does it mean to be arithmetic?
Add or subtract.
What's the common difference then? It's 5.
So like even by the time we're done with the problem, we can see the sequence after, and that's how we calculate it.
That's one way. I'm about to show you something else you can know too. Anytime it's an arithmetic sequence, this expression will have a number times n plus or minus another number. There's no squares involved. There's no multiplication of n times itself or anything like that. And do you see the common difference? What we would call the slope if we created this to be a line. The number that's multiplied by n.
So we'll always
That's
have
the common
that.
difference. It will. And so to answer your question again, yeah, you can look at your pattern that you created to tell that. Or you can remember that it happens to follow the right form. And either one is a perfectly fine way of thinking about it, right? So a lot of people recognize patterns better, and they're going to see after they create 11, 16, 21, 26, 31, they're going to see, oh, I just add 5 and put on my terms. And some people are going to say, oh, I remember that's got that right form. That form is the one that follows this pattern. And so how about the second one? Let's do the terms on that one. What's the first term? If I put in n equal to 1, what do I get? I do get 0. What if n is 2? I get 3. What if n is 3? I get 8. What if n is 4? I get 15. One more. N is 5? I get 24. So, let's rule them out one at a time. Is it arithmetic? No, because I would have to add 3 and then add 5, and then add 7, and then I add 9, which is interesting, right? But it isn't arithmetic. Is it geometric? Do I multiply by a term to give the next term? No, in fact, the first clue that it's not geometric is geometric would never have the number 0 in it. So what happens when you multiply 0 by any number? You get 0, so it won't pattern out with making you multiply with it. So it's not geometric, which means by default it's neither. It is an interesting sequence though, as we mentioned, because if you take a look, here I add 3, here I add 5, here I add 7, here I add 9. Take a look at this just because, again, we're supposed to be looking at patterns in this section. What if you looked at these numbers, 3, 5, 7, 9? They are all odd. They're increasing by 2, which means they're arithmetic, right? So what I just did is I found something called first differences. The first differences here are not actually common, right? It's not a common difference. But the first differences actually did determine another sequence that was arithmetic. And again, the reason that's happening is because this term was squared. Anytime you have a squared term, what's going to happen? Interesting, huh? So you might be thinking to yourself, okay, she didn't give me an example of a geometric one. So what would a geometric one look like in its form of an equation? If you had a geometric one, the equation would have this form. So if you have a geometric form, what it looks like is it looks like, let's say plus or minus a number. So for example, I could have 3 to the n plus 2. And now you see why we brought it back. So it's just all right. Geometric sequences are exponential functions, exponential expressions. I end up with the exponent being the variable. And you can take a look and you can see that that's going to work. So let's try it just for a minute with this one. What if n is 1? I get 5. What if n is 2? What is it?
11.
11. I'm beginning to think I'm not going to have that 2 on the end. But, oh, it isn't. I know what it is. I know what I'm doing wrong. Let me fix. I need a constant at the beginning. Here. Constant times 8 at the end. So it would have the form something like, let's do 2 times 3 at the end. This will work. That's what happens when you don't write it down and you just decide in the middle of class, hey, I should show them this. Doesn't always work out. Okay, so again, let's try it again. If n is equal to 1, what do I have? 6 on this one now. What if n is 2? We have 18. What if n is 3? Whoa. 27 times 2. It's 54, yeah. And if you keep going, what you'll notice is that to get from one term to the next, what am I multiplying by? 3. 6 times 3 is 18, right? And that's happening because 3 is the base of the exponent, actually. So, what we would call linear expressions generate arithmetic sequences. Exponential expressions generate geometric sequences. Is this inductive or deductive reasoning?
Deductive.
It is deductive. Caleb, do you really know why, or are you just assuming it's deductive? Yeah, I thought you were just trying to say that. It is deductive. Deductive reasoning means that you have a concrete, in this case, formula. And you're using that formula to create the pattern, right? I didn't have a concrete formula on the page before, on slide before. I just had some patterns that I was making generalizations about. Here, I've actually got an equation, or actually an expression. I've got an expression that I can use to create my pattern. This is actually deductive reasoning.
So it's not always a formula, it's always an equation.
Well, this is, we use those languages a little bit interchangeably. This is actually an expression. Equations have equal signs, and none of these have equals anything because they don't equal anything. We're plugging numbers into it, which is why we sometimes use the word formula as well. We use the word formula when we substitute or evaluate into it. So, expression is actually the most accurate term. All right. So I mentioned counterexample a moment ago, and you guys actually. This is my other class that I showed an example, a counterexample of something the other day. So if you take a look, one of the things that students like to do is they like to what we call cancel things out sometimes. And unfortunately, we use that word cancel far too often to mean far too many different things. Have I said this to you guys before yet? I didn't think so. So we use the word cancel when we say 5 plus negative 5 cancel out. We use the word cancel when we say 5 divided by 5 cancels out. Because we mean the same thing when I used it in those two different places. It didn't. One of them, quote unquote, canceled out to 0. The other one canceled out to the number 1. And we keep using this word cancel. It's not a very good mathematical term because we use it so broadly to mean so much. So if you take a look and you were to assume a child said, oh, n plus 5 divided by 5, I can cancel out the 5 over 5, and it will become the number 1, so it becomes n plus 1. Okay, so this is what this person, this child, has thought when they did this problem. So this actually says you want to find a counterexample. Counterexamples are great for showing incorrect reasoning in algebra. That's why we're seeing this happen right now. So what would a counterexample look like? Well, a counterexample means an example that shows that this won't work. In other words, you need to pick n equal to something. So tell me an n value. 3. All right, so if n equals to 3, what's going to happen? Well, on the left-hand side, I have 3 plus 5 over 5. And on the right-hand side, I have 3 plus 1. So what is 3 plus 5 over 5? 8 over 5. What is 3 plus 1? 4. And does 8 over 5 equal 4? No. And because you've provided a concrete example, that shows that this equation is not true. It is a counterexample. Now, here's what you have to be careful of. Whenever you create counterexamples, it is possible when you choose that n that you make a mistake and don't choose so well. What if instead of n equal to 3, one of you had said, well, let's try n equal to 0? Okay, well then I would have, on the left-hand side, 0 plus 5 over 5, which is what? 1. And on the right-hand side, I would have 0 plus 1, which is 1. And this is what students do all the time. They check to make sure that something works by trying one example. And if it works in that one example, they think it must be true all the time. Well, you have to be careful. We chose 2 different examples, and in one of the cases it worked, and in one of the cases it didn't. So what we're not saying is that this equation is never true. Be real clear about that. I'm not saying that there is not any number for which this works. We found one that did. N is equal to 0 works. It makes both sides the same and so forth. But what would have to be true, what has to be true if the conjecture is true, is that it works for every value. So a counterexample will show that it works. It does not work for some value. Now, this one's not too bad because most numbers you pick are not going to work. Right? But if you just so happen to pick the wrong value and it does work, that does not mean that the equation is always true. Okay? All right, let's see where we are. All right, I think we have time for the first slide of figured numbers. Figured numbers are fun. Okay, so figured numbers are numbers that are based on a pattern of, well, for lack of better words, a pattern of dots. So you have a geometric shape that kind of grows with each successive term, and you can count the number of dots and you can create a pattern based on that. So let me show you one. Triangular numbers look something like this. Here's the first term, if you will, in the pattern, a single dot. The second term has 3 dots, and all of a sudden you should say, oh, that's why I should call it triangular. Looks like a triangle. The third term looks like this. It looks rather like a pyramid, right? What do you think is going to happen on the next one? Yeah, there's going to be 4 on the bottom. So I have a pyramid that's growing every time. And could a child generate this pattern to continue it? Could they continue this generalization? Certainly. Now, these dots can be written with the numbers as well. So you can see listed below, I have the number of dots in each term. So right here, there's 1 dot, right? Here, there's 3 dots. So I've got 1 and then 3. Here, there's 6 dots. So I've got the number 6. If we count correctly, we'll have 10 dots on this one, and if we continue our pattern beyond that, we'll have 15 dots. What's happening every time? Well, I'm adding some dots, but I'm not adding the same numbers. It's not arithmetic, right? I haven't added the same number of dots to every picture. I've added another row at the bottom that has 1 more dot than last time. Yeah? So let's see if I got it counted right. So I had 1, and then I added 2 dots. And then from here to here, I should have added 3 dots, which I think that's true, yeah. And then from here to here, what do I add? I think I had 4 dots. And then I do this again, and I add 5 dots. So there's a couple things I want to observe with you. One thing I want to observe with you is that the original sequence is not arithmetic. Right? This is like the n squared minus 1 or whatever it was on the slide before. However, the first differences are arithmetic, aren't they? The other thing that's interesting to notice is that once we've established the numerical pattern down here, right? This is the fact that I'm adding 5, and the next one I'll add 6, and then I'll add 7, and then I'll add 8, and so forth. Once I've established that pattern, I don't need to keep drawing the dots if I don't want to. Yeah? I can say, okay, what's the, where are we at? Let's see, this is the first, second, third, fourth, fifth. I can say, what's the 8th term? And I don't need to draw more triangles to get there, do I? Well, what's the 6th term? What comes next? What would I add? I'd add 6 and it would be the number 21. What's the 7th term? What would I add? 7 and the number is 28. So what's the next term? 36. So I can generate the pattern without generating the triangular numbers, but the triangular numbers are the ones that are where we got the pattern. Does that make sense? Okay. So there's one more type of figure numbers, and that is, do I call it squares or rectangles? I think it's called squares. Square numbers. And they're uncannily just like square numbers you've seen before, but they have an image associated with them as well. We're going to save them for next time. Next class period, we'll finish these last 2 slides, and then you'll have a chance to do yours working class. So if we happen